this video, we are going to cover electromagnetic induction and Maxwell's third equation. Now, what this is all about is the idea that if we have a magnet that passes through a coil of wire, that magnet will actually induce a current to flow within the coil of wire, which can then go on to power all sorts of various things. So this is a pretty important and big part of electromagnetism. And let's go ahead and dive right into it. Now, in the last video, we talked about a coil of wire, which is also known as a solenoid right here. And we said that if we pass a current right here, I, through our coil of wire, then we get a magnetic field that looks something a little bit like this. It goes along the z-axis. If, this is our z direction right here, then we actually have a magnetic field that is pointing along the z-axis right here. And this is what happens when we have a coil of wire. But what happens when we kind of reverse the scenario? So instead of passing a current through, we have our coil of wire like we had before. But instead what we're going to do is we are going to get a magnet and we are going to pass this magnet through the coil just like this right here. So just a reminder, there's no current flowing through the coil this time, but we have a magnet and we're going to pass it through the coil right here. Then what happens? Well, we find experimentally that this in fact produces a current through the coil. And this is very different to this scenario right here, where obviously, the current was powered by a battery and this then went on to produce a magnetic field. But in this scenario, we have no battery whatsoever. We literally just have a coil of wire and we're passing a magnet through, and this produces a current that goes around the solenoid, just like the current here, the same geometry. Now, the fact that we have a current flowing must mean that there is some kind of voltage, some kind of potential difference, which is causing the current to move. Remember, voltage or potential difference is kind of similar to force, and current is kind of similar to velocity. But of course, we don't have a battery in this situation. So how do we explain what's going on? Well, what is really, really helpful to do is to actually zoom in to this wire and think about what's kind of going on a microscopic level. So we have a wire right here. So this is just kind of like a zoomed in part of our wire. And for now, we're just going to draw all of the electrons that are whizzing around within the wire. And these electrons are obviously what's causing the current to flow. Now, what actually causes charged particles to move on a fundamental level? Well, we already know the answer to that. Electric fields do. If we have an electric field right here, and we have a charged particle, be it positive or negative, then we know that a positive charge will move sort of in this direction to the negative side of the electric field. And likewise, a negative charge will move in the opposite direction, like that. So when we have electrons in a wire, when we're talking about a current, essentially we're just talking about a bunch of charged particles being accelerated by an electric field right here. Well, we know that the electric field is simply equal to minus the gradient of the potential, V, right here. E equals minus del V. This was an equation that we derived way back in electrostatics, and it was basically useful for evaluating a electric field given the electric potential of a point charge. But of course we can apply it to this situation as well, because we have lots and lots of charges. So how do we express this in terms of V? Well, to do that, it's actually very helpful to consider a really small piece of distance right here. And we're going to call this distance dl. So this is an infinitesimally small change in the length, a small section of our wire right here. Well, since we know that electric field is essentially the gradient of voltage, then it must follow that a small change in voltage is simply equal to minus the electric field times dl, as long as it's kind of in the same direction. And so to write this in terms of vectors, we can just therefore say that this is equal to minus E dot dl. right here. So that's essentially the same thing, except kind of a bit more applicable for a wire. So we're saying that the voltage is simply equal to the electric field multiplied by whatever distance the charged particle is accelerated through by the electric field. So far so good. So what I'm going to do is I'm going to take one loop of this solenoid, and for now I'm just going to pretend that it's closed right here. So this is kind of the simplest solenoid we can get. And we have a closed loop right here. And of course we have our magnet that we're passing through, and we find that our magnet is passing through, and therefore we get a current. This is what we observe. So what is the value of the voltage, in quotes, over the entire loop? Well, the total voltage is just going to be the integral of all the little voltages, dV, right here, over the closed loop. And we said that this is just going to be equal to minus E dot dl right here. Now it's important to note that for the most of the time, this will just be zero right here, because of course you have a closed loop and there is no battery or anything that's causing there to be any kind of electric field. So therefore normally this would be zero. But of course in this case we don't have zero, because of course we know that there is a current that's flowing around the wire. And so we define this term epsilon as being equal to minus the integral of our voltage right here. And so this is equal to minus the integral of E dot dl around our closed loop. And so we simply end up with epsilon is equal to our closed integral of E dot dl right here. Now, what is this epsilon that I've just defined? Well, epsilon is basically saying that even though there is no kind of battery or anything along this loop, there is still an effective potential difference. And we call this the EMF. And this stands for Electromotive Force. Now, one important thing to note is that the electromotive force is not technically a force. It's not measured in newtons. It is a voltage. It's a potential difference. But you can essentially think of it as a bit like a force, because it's a force that's produced, which therefore causes a current to flow in this wire or part of the solenoid right here. Now, some of you may have come across the term electromotive force before when dealing with internal resistance. And yeah, this is kind of essentially what it is. It's kind of the same thing. The electromotive force is basically just the intrinsic potential difference that's produced by any closed circuit right here. And that is what drives the current to flow around. It's the fundamental voltage that is produced by any kind of battery in any circuit right here. But of course, in this case, we don't have a battery. We just have an effective battery, if you like, which has a voltage which is equal to epsilon right here, the EMF. Now, when I have this magnet right here and I pass it through this loop, what I find is that I get a current whenever I am moving it in and out right here. And the amount of current that I get is, of course, proportional to how quickly I move it. So if I move it quicker, I actually get a greater potential difference, and therefore I get a greater current. But if I keep it still within the loop, then I actually find that I get nothing. I get no induced EMF. So I only, again, like with magnetic fields, I only get a magnetic field as long as this magnet is moving through the wire. If there is no movement, if it just simply stays still, then I don't get any induced EMF. And this kind of effect right here is known as Faraday's Law. And mathematically, you can write this as the EMF that is induced as a result of moving this magnet back and forth is proportional to the rate of change of the magnetic flux right here, d phi m by dt. And this phi m is the magnetic flux. And that is, of course, as we defined before, equal to the magnetic field strength over the surface, integrated over a certain surface. And it's important to bear in mind that this does not necessarily have to be a closed surface. And in this case, it very much isn't a closed surface. This is an open surface. And you find that the magnetic flux is equal to the magnetic field strength integrated over the entire area. and the EMF that's produced is proportional to the rate of change of flux. Now, as well as this, it's important to note that there is in fact a minus sign right here. And this minus sign is actually very important, and it's also known as Lenz's law right here. And the best way to understand why there has to be a minus sign right here is to kind of think about what would happen if there wasn't a minus sign. So let's go ahead and think about what we're doing. So we have a coil of wire right here, and we have a magnet right here that we're passing in and out. Now, when I move this magnet through the loop, then of course I get a current flowing in the loop right here. But what did we say before whenever we have a current flowing in a wire? Well, a current flowing in a wire will give us another magnetic field around the wire. So if we just draw the little rings, which we showed in the last video, that these magnetic fields are, they're closed loops that kind of orbit the wire, then we have a magnetic field that is produced by the wire. And the key thing is that the direction of the magnetic field has to be in the opposite direction that this magnetic field is producing, because of course this magnetic field lines, they run from north to south. So if we have a magnetic field like this and we're passing it through, then these magnetic field lines must be in a direction which is opposite to the direction of these magnetic field lines like that. Now, suppose it didn't work like that. Suppose that they were in the same direction. Well, when I move this magnet through, this will cause a current to flow, which will therefore produce a magnetic field around the wire, around here. If it was in the same direction, that magnetic field would accelerate this magnet even faster, and it would cause the current to increase even more, making this magnetic field around the loop of wire be even bigger, causing this to be even faster, causing an even greater current, causing an even bigger magnetic field, kind of spiraling out of control. It would essentially self-perpetuate, and you would end up with basically an infinite scenario where you essentially have an infinite current and an infinite magnetic field. So if these field lines are in the same direction as these field lines, then essentially you break the laws of physics, and you're not allowed to do that, of course. And so you therefore say that the induced EMF produces a magnetic field as a result of the current flowing, which opposes the change that caused it. And this is known as Lenz's law. So let's go ahead and write this out again. So our EMF is equal to minus d phi m by dt right there. But we also said that this phi m is simply equal to b dot ds integrated over a surface right here. So we can also express this as minus d by dt times the integral of the magnetic field over the surface right here. But what is epsilon? Well, epsilon is just equal to the closed loop integral of the electric field around a closed loop. So let's go ahead and write that in. We're going to get our closed loop integral of E dot dl is equal to minus d by dt of B dot ds right here. This right here is Faraday's law of induction, and it is also Maxwell's third equation, and it's written as an integral form right here. So this is a very, very important result. This is the integral form of Maxwell's third equation. And like we've been doing with Ampere's law and Gauss's law, we've been converting it to the differential form by applying either the divergence theorem or Stokes's theorem. And in this case, because of course we have a surface, we are actually going to apply Stokes's theorem. So whenever we have a line integral, we can convert this to a surface integral using the fact that the curl of E dot ds integrated over a surface is equal to the line integral of E dot dl. So this is Stokes's theorem. And this is of course equal to minus d by dt of B dot ds right here over the surface. And these two integrals are over the exact same surface. So essentially we can just remove the integration and write that the curl of E is equal to minus dB by dt. And this is the differential form of Maxwell's third equation, or the Faraday-Lenz law right here. So this equation powers the entire national grid. So it's a pretty important equation. And this will basically tell us that if we have a magnet that's moving in the vicinity of charge, then we get an electric field that is induced. And the direction of the electric field is going to basically be similar to Ampere's law, kind of at right angles, tangent, like sort of perpendicular, hence this kind of cross product curl term right here. Now, it's important to note that there are in fact some key differences between induced electromagnetic fields, like found in this equation right here, and electrostatic fields, which is what we've been dealing with at the very start of this course when we were talking about Gauss's law. And the first thing I want to kind of consider is conservative versus non-conservative fields. Now, for any vector field to be what's known as conservative, that basically means that you can, say if you want to go from point A right here to point B, then for a conservative field, it doesn't actually matter what journey you take from A to B, so whether you took that journey in space or whether you took this journey in space. If you were to sum up, say, or integrate, because it's continuous, the field F along the line, along the path right here, you'd get exactly the same for path A as you would for path B. So it doesn't matter which path you take in a conservative field, you'll get the exact same result either way. However, this is in fact not the case for a non-conservative electric field, and this induced EMF right here, epsilon, which is equal to the closed integral of E dot dl, this is obviously not going to be conservative because this value of epsilon, of course, goes over the same path because it's a closed path right here. So even though the path would be exactly the same, you can get a different EMF depending on, well, how quickly the magnet moves through this kind of circuit or this coil of wire or this loop of current. So that's one important difference to note between electrostatic fields, where if you just have a point charge right here that's emitting an electric field that's radially outwards, and then I have a test charge just somewhere in space, and if I'm moving it from where it is right here, we'll call it point A to point B, then it doesn't matter whether I move it around this direction, take this path right here to point B, or whether I go in this direction right here, take this path to point B, the electric potential or the amount of work done will still be the same. So basically this is one key difference between induced electric fields and electrostatic fields. And the other key difference between the two types of fields is that whenever we have an induced electric field, the electric field lines that result are always closed loops. So, because of course this is a closed line integral right here. And this is of course in contrast to electrostatic fields, where of course electric field lines run from positive right here to negative right here, where obviously you have the arrows pointing from positive charges towards negative charges. So of course that's the case for electrostatics, but for an induced electric field right here, then whenever you get a magnet passing through, the electric field lines will always be a closed loop, which is of course at right angles to the direction of the magnet, where you're moving it through the loop and then out of the loop right here. So that is another key difference between induced electric fields and electrostatic fields. Now, I'm going to go over a couple of examples of devices, you could say, that rely off of Maxwell's third equation, that is curl E is equal to minus dB by dt. So for our first example, we are going to consider what's known as a slide wire generator. And basically all this is a rectangular kind of loop of wire. So I'll draw this in orange right here. This is essentially a rectangular loop, but at some point you actually have this kind of bar right here. And this bar is actually free to move along this axis right here. So along the horizontal axis, we're actually free to have a bar which can move up and down like this. So this could be, you know, somebody just grabbing the bar and then moving it right here. Now, what we're going to do is we are going to apply a magnetic field, which we're going to do in yellow. And this magnetic field is going to be into the plane of the diagram. So we have this B field right here going in to the plane of the diagram. And what's going to happen? Well, because of course we have a magnetic field and a loop of wire that kind of is perpendicular, then we're going to get a current flowing through this wire right here. So it's going to be a circuit that flows through the wire. And of course, since it has to be a closed loop, because of course we said that induced electric fields have to be closed loops, it's going to flow through here, through the bar and complete the circuit like this. But of course, when we move this bar, then we're actually going to enlarge our circuit. So how do we figure out how much current or EMF is induced from, like, say, how fast we move this bar right here? Well, we know that if it's a constant velocity, then we can say that any kind of change in displacement, dl, is equal to the velocity times dt right here. And so if we say that this kind of is the dl right here, then we can say that this infinitesimal change in length along the horizontal axis is equal to the velocity along the horizontal axis multiplied by an infinitesimally small change in time. But of course, since we have a loop, then not only will this distance between, say, here and here change, but the entire area will in fact change of this enclosed area that the circuit is enclosing right here. So we can actually write that the change in area, ds, is equal to whatever this length here is, which is of course a constant in time. So let's just go ahead and call it capital L right here. And we can say that this is multiplied by an infinitesimal change along the horizontal axis, which is equal to v times dt right here. Now, because we have a changing area with time, we can see that this right-hand side of the equation, d by dt of b dot ds, even though b is not changing with time, is going to change. And therefore, we are going to get an EMF, hence our observed current right here. So let's go ahead and substitute in for ds. So we're going to get that the EMF is equal to minus d by dt of the integral over the surface of b dot ds. But we know what ds is, so let's go ahead and substitute this in. Lv times dt. And of course, since b is parallel to the surface normal vector, then we can of course just remove the vectors from this. And so we get this equation right here. But we're just differentiating and integrating over time. So let's just go ahead and just remove that. So we're just going to go ahead and get epsilon is equal to minus BLV right here, because of course we're just differentiating and integrating this term over time. And so this right here is telling us what the EMF is, the induced EMF, as a result of moving this bar horizontally, and therefore it's sweeping out an area. And because there is a change in area, even though there's no change in the actual field that's being applied, we're going to get a change of magnetic flux and therefore a change of EMF. And of course the direction of the EMF will be given by Lenz's law, and that will give you the direction of the current. And this will of course be opposing the change that causes it. So in actual fact, when you move this wire, you will actually experience some kind of like a resistive force. There will be an induced magnetic field so as to oppose the change that causes it. And the final example we're going to consider is what's known as an alternator. And essentially this is what powers the national grid. It's essentially a rotational turbine where of course you have some kind of steam, say, that's kind of like causing a turbine or causing some kind of rotation to happen. And the act of this spinning, this rotation, is what's causing there to be a current generated. This rotation is causing a change in the magnetic field, therefore a change in the magnetic flux, which therefore induces an EMF right here. So what we're going to consider is we're going to consider a kind of a rectangular loop like this. This loop, of course, is going to be connected to terminals right here. We are just going to be considering a loop of wire, and it's going to be spinning along this axis right here. So this is the central spinning axis, and we're going to go ahead and say that it's spinning with an angular velocity of omega right here. And we're going to go, and of course, angular velocity is defined as the rate of change of the angle with respect to time right here. So if omega is constant, which in this case we're going to say it is, then we can go ahead and write that the angle theta is equal to omega times t right here. So if we want to get the angle that's swept out in a certain time t, you multiply it by the angular velocity. What's the EMF we're going to get from this? Well, let's go ahead and write out the EMF equation. So we're going to get epsilon is equal to minus d by dt multiplied by the integral over the surface of b dot ds right here. Now, if we have our magnetic field as before passing up like this, so I've kind of drawn it slightly differently this time rather than drawing it in the plane. I've actually tried to draw it in 3 dimensions. And so we have a magnetic field that's being applied right here. We're obviously having a rotating coil, which is going to cause there to be a change in magnetic flux and therefore an EMF. So how do we quantify this angle right here? Well, because of course it's rotating, the area that's exposed to the magnetic field will be, of course, oscillating in time. And how will it be oscillating quite? Well, it will be oscillating sinusoidally, just like this. So if we say at the very start of our period, our kind of loop of wire is directly facing this magnetic field, which is this situation I've drawn right here, then of course we're going to get the maximum amount of flux passing through. The maximum amount of magnetic field lines will be cutting through the surface. But say I am to consider this part of the cycle right here. So here is our axis right here. I've drawn it a little bit off, unfortunately, but our magnetic field is still in the same direction. We're not changing the direction of the magnetic field, but of course the loop of wire has changed by 90 degrees. It's now vertical, just like the magnetic field. Well, of course, the normal vector to this surface is now going to be at right angles to the magnetic field, and therefore we're going to get zero flux. So what we can write is that we can write that the angle as a function of time is equal to the cosine, if we're starting with it in this position right here, this orientation, of omega t. So how do we write this in our integral? So we say that this is equal to minus d by dt. Well, what is this total flux right here, b dot ds? Well, we know that b isn't in fact changing, so we can just simply write b as being a constant out the front. And in fact, the actual surface area isn't changing either, because of course we have a constant surface area. It's just the direction of the in which the surface area is facing is changing. So we can write this s right here, but of course we need to factor in this angular dependence, where of course, you know, the angle is going to matter with how much magnetic flux we're getting. So we're going to get cos of omega t right here. So all we now have to do is we have a derivative right here of a cosine function. And so if we differentiate this with respect to time, we get bs times the derivative of cos is minus sine, but we're going to get another minus sign cancelling out the front right here, times sine of omega t, but of course we now have to bring out a factor of omega due to the chain rule. And sometimes rather than just having one loop of wire right here, we might in fact have many stacked on top of each other for, you know, the current multiplying effect, because of course if we have the same thing repeated over and over again, we get more and more current, just kind of stacked on top of each other. If we think about what the total EMF is, then we say that the total EMF is just the number of turns in this loop right here, multiplied by all of this stuff right here. So quite a few terms in this equation, but we get that the induced EMF is equal to n omega b times the area times sine of omega t. And probably the most important thing to note in this equation is this sine of omega t right here. And of course that is slightly different to the cos of omega t that we get for our theta dependence. And what that basically means is that the EMF, the induced EMF, is 90 degrees out of phase with the total flux that's going through the loops right here. So to kind of illustrate what that actually physically means, if we have our loop which is constantly spinning, even though at this orientation we get the maximum amount of magnetic field passing through the surface right here, if we were to measure the EMF at this instant in time, because of course it's spinning, then we would actually find there is in fact zero EMF at this moment in time right here. And conversely, if we were to measure the EMF at this moment in time, when of course the magnetic field is not cutting the flux at all, then you actually find that you get the maximum EMF. So it is 90 degrees out of phase with the magnetic flux. And so if you were to draw a plot of both graphs, so the magnetic flux will do something like this. It'll be a cosine function. So it'll start off at the maximum and then oscillate like this. But if you were to measure the EMF at the exact same time, then you get a sine function as we just derived right here. So it's in fact going to be like this. So it's going to be 90 degrees out of phase, something like that. So this is the EMF and this is our total magnetic flux. And sometimes you in fact call, when you have multiple layers stacked on top of one another of coils, you sometimes call it the flux linkage. And normally we'll see this N included in the equation just because you have to normally factor in the number of turns. And one final example I just wanted to illustrate, and there's not really much maths. I'm not going to do any maths with this at all. It's just to kind of illustrate how just quite how sort of multifaceted electromagnetic induction is with a metal detector. So a metal detector is of course a sort of pad which you essentially have mounted on the end of a stick right here. But the important thing is this kind of pad area right here. And you scan the ground with this pad and it starts beeping as soon as it's detected any metal. And so the way in which this kind of works physically is, so say we have our metal detector and we have a piece of metal that's in the ground right here. So what actually happens is you send a pulse of current around this loop right here, and that is applied by a transmitter from here. It basically says, let's produce a pulse of current that goes in here. And what actually happens is that when, of course, we have this pulse of current, this generates a magnetic field that, of course, goes in this direction because it's, of course, perpendicular. And this magnetic field will actually link up with this metal right here. And what happens when we, of course, have a changing magnetic field in this metal right here? Well, our changing magnetic field is going to induce a current within the metal right here. And this is known as an eddy current, and it's basically a circulating current that is produced by an external magnetic field. And of course it will be in a swirly kind of formation because of course the magnetic field is in this kind of up and down vertical axis right here. But of course this eddy current right here, this induced eddy current, will in fact produce another magnetic field kind of in response to the magnetic field that was sent down by the metal detector ring. And so therefore you're going to get a entirely new current, which will of course be in the opposite direction because of Lenz's law. And I'm just going to go ahead and call that I dash, or you can sometimes see it called I nu or something like that. And so if basically you get a reduced current from this initial pulse, which of course you know the current before, then essentially that means that you found a metal, because of course this metal has induced a current back to the ring of our metal detector, and that has reduced the current, and so therefore you know when you have a current. So if you were to watch a reading of the current and you find sort of nothing really, and then you find there's a sudden dip in the current, then you know you found a piece of metal, and then it will start beeping. So that is how essentially metal detectors work. So I hope that was really informative, and I hope it was good to have a couple of those examples of the changing magnetic field just to illustrate quite how versatile Maxwell's third equation is. So yeah, see you guys in the next video.